So, in the last session we proved that the maximal function satisfies certain weak type estimate, in the sense that the set where the maximal function is greater than alpha, that set, the measure of that set is controlled by L1 norm of f divided by alpha. So, we will use that crucially to prove what is known as the Lebesgue differentiation theorem. Okay. So, that is the aim in this session. Okay, let us start. So, let me straight away state the theorem, okay, so, and then we can explain things. If f is in L1, okay, then limit r going to 0 1 by mod bx r. So, remember modulus is simply the Lebesgue measure of the ball, and you integrate f now, not mod y, mod f, just f, the average of f, okay, average of mod f, and then you take supremum, you get the maximal function, right. But this is simply the average of f that will converge to f of x almost everywhere, okay, as r goes to 0. So, this is what we started with, the limit of 1 by 2 r x minus r x plus r gt dt, let us say. This is g of x, right, if g is continuous, but we are saying that even if it is in L1, this happens almost everywhere. Okay, so, that is why it is called the differentiation theorem. Okay, so, we will prove this. This is not very difficult now that we have done the hard work of proving that the maximal function satisfies certain weak type estimate. Okay. So, enough to show that ETST means enough to show that if E alpha, so again I am using E alpha for a different set, you look at the set x where the lim sup of the difference, okay, so lim sup of r going to 0 modulus 1 by the measure of the ball average of the function f I dy. I want to show that this converges to f of x, right. So, you simply look at f of x. So, for each x this is a function of x, right, for each x you get a value, and I am taking the lim sup of the difference, right. Okay. So, if E alpha is this, okay, well where is the alpha? So, let me write down the alpha here as well. This greater than 2 alpha or 3 alpha, does not matter what some constant times alpha, okay, we will see whether it is 2 alpha or alpha by 2. If you look at this set, then we want to show, then well enough to show that, we started with enough to show that. So, then the Lebesgue measure of E alpha is 0. So, if this is true for every alpha positive, right, then wherever, so you can take, so this is enough. Why is this enough? Well, this is the usual standard procedure. So, if I take E to be union E, let us say 1 by n, right. So, I am taking alpha to be 1, 1 by 2, 1 by 3, etc., right. And so, each E by E 1 by n has measure 0. So, measure of E also will be 0, but measure of E, what is E? E is the union, which is simply all those points where lim sup are going to 0 modulus of whatever is written greater than 0, right. If this has measure 0, the complement, which is where the lim sup is 0, is a set of full measure, and on that set we have convergence, right, because lim sup is 0. So, lim inf also is 0, and so 0. So, it is enough to show, it is enough to look at this set and prove that it has measure 0. Okay. So, first thing to notice that if, so note that if g is a continuous function with compact support, okay, then this is trivial, then 1 by the measure of Bxr integral over Bxr g y dy, this converges to g of x as r goes to 0 for every x in Rn. Okay, so there is no almost everywhere statement because f is g is a continuous function. Okay, so that is a trivial statement. Well, what do? You look at the difference. You can look at the difference of bx in a modulus of bxr integral over bxr gy dy minus g of x. Right, g of x is a constant as far as the integral is concerned. So you can take it inside because of this factor here. So this is bxr integral over bxr. You can look at gy minus gx dy. Okay, so if I take the modulus, so that will be less than or equal to, I take the modulus inside, and this I can make less than epsilon as small as I want if r is small enough, right, because of the continuity, and what remains is integral bxr bx divided by the volume of bxr, which will get cancelled and you will get epsilon. So this is less than epsilon for all small r. Okay, so that uses only continuity, but they are dense. So we have a dense subspace in L1, right. CCRn is dense in L1 of Rn with respect to the Lebesgue measure. Okay. Okay. So what do? So choose, so fix epsilon positive, choose g in Cc of Rn such that remember our f is in L1, so I can approximate f by a continuous function with compact support. This is an epsilon. This is possible. Okay. So now, well, our aim is to find out what happens to the limit of averages of f, right. So right, the 1 by the volume of bxr integral over bxr fy dy minus f of x. This is what we want to find out, right, whether it is 0 almost everywhere or not. So we bring in g inside, we look at, because we know how to control f minus g, right. So we bring in g inside. So write this as 1 by modulus bxr, okay, integral over bxr, okay, fy, fine, minus gy dy. Okay, so what did I do? I brought in g, right, with the integral. So I have to cancel that. So let's cancel that first. 1 by mod bxr integral over bxr gy dy. So that gets cancelled, right? The g's gets cancelled and I have just the first term. Okay, but this I bring in g of x, okay, and then I have to cancel that, plus g of x, right. So everything, so this term gets cancelled with this term gets cancelled with this term, and I have only the first term remaining, right, and I have f of x here, so minus f of x. Okay, so I have only added integral of g, subtracted that, and added g of x and subtracted that. Okay, so that it doesn't change anything. So if I take the modulus on the left hand side, so okay, so let me write one step extra here just to be clear. So modulus, so if I look at modulus, so that is the usual modulus, not the Lebesgue measure, modulus of this quantity fy dy minus f of x, which is what we want to estimate. This is less than or equal to sum of 3 terms, right. What are the 3 terms? One is 1 by bxr, the Lebesgue measure here, integral bxr modulus of fy minus gy dy, okay, plus whatever we know that already goes to 0, right. So we know that this, for a continuous function with compact support, the average minus the function value, right, that we know this goes to 0. So I have kept this as it is, plus whatever is remaining, mod gx minus f of x. Okay, very nice. This is of course, so when I take the lim sup, so lim sup as r going to 0 of this quantity is less than or equal to, I take the lim sup of that, lim sup of this is bounded by the supremum of these things, supremum of these things is the maximal function, right. So this is the maximal function of, you look at f minus g, instead of f you will be looking at maximal function of f minus g at the point x, right, plus lim sup of this is 0 because for g we know convergence takes place, right, and you have this one which has nothing to do with the supremum or the infimum, right, x is fixed. So these are constants. Okay, so now let us look at this again. We are trying to estimate this set E alpha, right, estimate the Lebesgue measure of this set. This set is the lim sup of something greater than 2 alpha. Okay, that quantity is what we have got here. So we are looking at the set where this the lim sup of this is greater than 2 alpha, right. So that will be contained in the set where this is greater than alpha and this is greater than alpha, correct. I am adding two things. So something is, the sum is greater than 2 alpha is of course contained in the set greater than this one component greater than alpha, the other component greater than alpha. Okay. So the measure of E alpha, remember E alpha is the set where the lim sup is greater than or equal to 2 alpha, that is contained in the set where the maximal function of f minus g at x is greater than alpha, okay, union maximal the all those points such that gx minus f of x modulus is greater than alpha. Because if this is greater than alpha, then one of them, it has to be contained in this, because if both of them on the right hand side is less than or equal to alpha, the sum will be less than or equal to 2 alpha, and so the left hand side will be less than 2 alpha. That is why. Okay, so well, so I should write E alpha first and then take the measure, right. So the set E alpha is contained in the union of this set and this set. Okay. So the measure will be less than or equal to sum of them, right. So measure of E alpha, which is what we want to compute or bound, is less than or equal to the measure of the set where the maximal function of f minus g is greater than alpha plus the measure of the set where mod gx minus f of x is greater than alpha, okay, which of course is less than or equal to this we already did, right. That is a Hardy-Littlewood maximal theorem. It says that maximal function of an L1 function where it is greater than alpha, the measure of that is controlled by L1 norm of the function divided by alpha, right. There was a 3 to the n. So we had 3 to the n by alpha times L1 norm of f minus g, right. Now the function is f minus g, not f, plus, well, how do you estimate this? Well, this is the indicator of this function, this set, right, dm. On the indicator, so this we have seen, this is called the Chebyshev inequality. I know that this is less than or equal to Rn mod gx minus f of x divided by alpha, because that is greater than 1 on that set, and I change the integral to Rn, right, dx. So that is 1 by alpha times g minus f L1 norm, right. So I have 1 by alpha times L1 norm of f minus g, okay. But I know that this is, well, we chose g in CC such that this is less than epsilon, right. These things are less than epsilon. So I have, this is less than or equal to 1 by alpha times 3 to the n epsilon plus epsilon, right, goes to 0 as epsilon goes to 0. I can make epsilon as small as possible fixing the alpha. So this tells me that the measure of E alpha is 0 for every alpha, implies outside the set union. So implies E equal to union E 1 by n. Remember the E 1 by n's. E has measure 0, and on E complement we have convergence, right. On E complement limit of r going to 0, integral 1 by modulus bx r, we write it in limit r going to 0, 1 by the volume of bx r, integral over bx r fy dy converges to f of x. Okay. So on E we do not know, but on E complement it converges. That is precisely the convergence almost everywhere. Okay. All right. Okay, so this calls for a definition. So now we can write it as a definition. A point x in Rn, okay, is called a Lebesgue point, or Lebesgue density point if you like, Lebesgue point of some function f in L1 locally integrable L1 functions Rn if, so remember this means that integral over f k mod f dm is finite for every compact k, right. Over compact sets it is integrable. If the following thing happens, the volume of Vxr and I have the integral modulus of f of y minus f of x. Okay. So, we dealt with this until now without the modulus, that goes to 0 as r goes to 0. Okay. So, that is what is meant by a Lebesgue point. So, well, this of course implies that, so recall that this implies, this is something which you have seen earlier in terms of convergence in L1 and integral convergence. If I look at the averages of f, which is what we were dealing with so far, fy dy, this will converge to f of x. If x is a Lebesgue point, so if x is a Lebesgue point, then we have this convergence. Okay, because when I look at the difference and take the modulus inside, I will get a bigger quantity, and that is this quantity which goes to 0. Okay. Okay, so here comes our corollary for the theorems we have proved. If f is in L1 locally integrable functions on Rn, then almost all points are Lebesgue points. Almost all points are Lebesgue points. That means you have a set for any f in L1 log, there is a set E where E has measure 0, and outside E all points are Lebesgue points. Okay, so let us prove this. So for the proof we will use all that we have done so far. Okay, proof is not very difficult. So first apply the theorem. So apply the previous theorem. Okay, so we will start with the assumption that f is in L1 and then we will justify. Okay, assume f is in L1 first. Assume f is in L1 first. Okay, not locally integrable, it is in full L1, and then we will apply previous theorem. Okay, and then apply previous theorem to g of y equal to modulus of f of y minus some r, okay, where r is a rational number. Okay, so well, maybe instead of r let us use p. R will stand for the radius. Okay, so let us use p minus p, where p is a rational number. So what do we know? We know that if I look at the average of g 1 by mod bxr, right, average of gy dy. This I know converges to g of x, right, almost everywhere. Okay. So that gives me, so this tells me limit of r going to 0 1 by mod b0 r, b0 r or bx r does not matter, integral over bx r, but g is the modulus of fy minus p, right. So mod fy minus p dy, I know it converges to g of x, converges to g of x, so that is mod fx minus p, right, almost everywhere. Okay, so almost everywhere meaning for x in let us say EP complement with EP measure 0. So for each p I have an EP, so that the measure of EP is 0 and outside EP the convergence takes place, right. That is precisely what we proved, right. If I fix the function, I have a set of measure 0 and outside the set of measure 0 we have convergence. Okay. So take E to be union EP. So for each p I do this, p in q, but this is a countable union, right. So union EP has measure 0. Okay. So if x is not in E and f of x finite, so there are two things here. X is not in E, so E has measure 0, so there is no problem. F of x finite, but f is assumed to be in L1, right. So f of x is finite almost everywhere. So these two conditions tells me that except on a set of measure 0 this will be valid, right. So this is a almost everywhere condition. Okay. So we take an x such that this happens. So f of x is finite meaning there exists a rational which is very close to it, right. So mod f of x minus p will be less than epsilon, right. So let us say less than epsilon. So fix an epsilon first of course. So fix epsilon positive. Okay. If x is not in E and f of x is finite, so understand this very clearly. E has measure 0. F of x finite means because f is in L1 it is finite almost everywhere. So we are only leaving out a set of measure 0, E and the set defined by f where f may be infinite, right. So you leave out those two sets, outside that f of x is finite, and if I fix an epsilon there is a rational such that f of x minus p is less than epsilon. So we get from this we get 1 by modulus of b0 r integral over bx r mod fy minus f of x. So I am trying to prove that x is a Lebesgue point. So I want to look at this and estimate it and see whether it goes to 0, right. So I bring in the rational p here into the integral and then divide split it. So this is less than or equal to, so let me write one line combining two steps. Okay, integral bx r mod fy minus p dy plus mod f of x minus p. Okay, what did I do? So I brought in p here, right, that is all, minus p plus p, and then I split the integral. Okay. So now we are in good shape because we can take the lim sup, right. So lim sup of the left hand side. Okay, so write this here. This is less than or equal to, well, what do I know about this? Okay, forget about that first. Let us look at this. This I know is less than epsilon, right. So this is less than epsilon. So this part is less than epsilon. What do I know about this? F of, so we just, so look at this statement we started with. As r goes to 0, the radius goes to 0, I know that this becomes smaller and smaller, right. It converges to f of x minus p. So it converges to f of x minus p. So this is a sequence which will converge to f of x minus p, right. So this converges to mod f x minus b. Okay, but both of them is less than epsilon, so I can say this is less than to 2 epsilon. So lim sup of, if I look at the whole thing here, that will be less than or equal to 2 epsilon, which is precisely what we want, right. So let me write that as one line. So what we have just proved is modulus b0 r integral over bxr mod fy minus f of x dy, right, lim sup as r goes to 0 is less than or equal to 2 epsilon. Okay, and so this, well, there is no dependence on epsilon on the left hand side, so it will have to be 0, which is same as saying that almost all points are Lebesgue points, right. So because the Lebesgue points are, x is called a Lebesgue point if this goes to 0, right. And what we have proved is for all those points which are not in E and not in the set where f takes value infinity, right. So that is a set of full measure, right. The complement has measure 0. So E and the set where f is infinite has measure 0. Outside that set, I know that this limit is small. It can be made as small as you want. Okay, so that is a set of Lebesgue points. So all those points are Lebesgue points. So they are all, so Lebesgue points for L1 function. So we remember we started with L1 functions, right. This is a strong assumption, but it's very easy to change it because the way we are taking averages, right. So let me draw some pictures and justify this. So if I have some function, I can always restrict it to some ball of radius big R. Okay, so if f is in L1 of locally integrable functions on Rn, then f times the indicator of ball of radius r, right, this will be in L1, and so the theorem will be true for this function. Okay, so in this ball there is a set, let us say E sub r, right, whose modulus is 0, modulus meaning the Lebesgue measure, such that ER complement intersected with VR consists of Lebesgue points. Lebesgue points, right, Lebesgue points for the function chi b 0 r times f. Okay, that doesn't matter, but once the balls are inside this, then it is integral of f, correct. So they are all Lebesgue, so these are all Lebesgue points of f as well. Okay, Lebesgue points of f as well, because once the balls are completely inside the bigger ball, the averages would be averages of f. There is no chi there because chi is 1 there. So instead of r, you choose r equal to 1, 2, 3, etc. So you will get E1, E2, etc. These are sets with measure 0, right, and the Lebesgue measure of the union is 0. So outside, so let us call that E. Okay, so on E complement, any point is a Lebesgue point. Any point is a Lebesgue point of f, right, because any point there is inside some ball, and in that ball it is a Lebesgue point of f because of this. Okay, so that is a standard argument because of the sigma compactness we have seen. Okay, so we'll stop here. So we proved two results. One was the Lebesgue differentiation theorem, which said you can actually integrate an L1 function and differentiate, right. So that is by taking averages of the function over balls and letting the balls, radius of the balls go to 0. Then you get back the function. So that generalized whatever you know from fundamental theorem of calculus in some sense. You integrate a continuous function and differentiate it, you will get back the function. And we also proved that almost all points are Lebesgue points. So one thing to note is that on the Lebesgue, so the Lebesgue points, they tell you that the function is well defined there. Okay, you don't have to look at f of x, you can look at the limit of the averages. The averages are integrals. So, whether you change f almost everywhere or not, it does not matter, right. So, there is a well defined collection, well defined set or the Lebesgue set on which f can be thought of as a well defined function. So, the value of f is sort of fixed there, even though you can change the value on any set of measure 0. Because of this Lebesgue points, you can choose a representative for which the values of the f at Lebesgue points are sort of well defined. Okay. So, that is the advantage of having Lebesgue points. Okay. So, we will stop here.